In this video, we're going to learn about the first derivative test, and that's a way to find the locations of relative maxima and minima on a curve. As with all my videos, in the description down below, there will be links to the times of the different slides, so if you want to skip a slide or go back to one you've seen before, you can click those links. Alright, let's dive right in. So before we start and actually see the test, let's go over a few definitions. And the first definition is going to be, what do I mean by extrema? And I use this sort of A at the end to pluralize. Some people use extremes. Doesn't matter. I've seen both. But these are just the highest and lowest points on a curve. And we have a few ways to specify these. So we can have what's called a relative, or also sometimes called a local maximum. And this is just the highest point in some open interval. The open's important. I'll talk about that when we see some examples, or I might talk about it in this slide. Algebraically, I can say this. So f of x naught being a relative maximum implies that f of x naught is greater than or equal to all f of x for these x's in some open interval, and this interval contains x naught. Now, that's relative or local. If I said absolute, or sometimes called global, maximum, this is the highest point on the curve. Pretty much anywhere. So f of x naught is greater than or equal to f of x for any x in the domain of f. Now, I have these maxima. I also have minima, so we have relative minimum and absolute minimum, and they behave exactly how you would imagine. They are the lowest point on some open domain and the lowest point on the entire function. Okay, one other term is this, critical point. And a critical point is just the point where the derivative is equal to 0, or where the derivative is undefined. And the important thing about this is all extrema are on critical points or endpoints. So if I can find these critical points, the endpoints will not be hard to find in most cases. I'll show you an example of that, example 2. I can go back and find whether we have, so I can find the critical points, go back and find whether we have an extreme point there. Okay, the first derivative test. So basically what this says is if f of x is continuous at x naught and f prime of x changes from positive to negative over x naught, f of x naught is a relative maximum. And that should make some sense. Now, if it's changing from positive to negative, either f prime has to hit 0 at x naught, or it has to be undefined, so as would happen in a corner or cusp. And you can see, okay, let's just consider that this point here is x naught, f of x naught. And if f prime is positive on the left, that means it's increasing. If it's negative on the right, that means decreasing. You can see we have a maximum. And I guess this would be inversely, or almost inversely, if f of x is continuous at x naught and f prime of x changes from negative to positive over x naught, f of x naught is a relative minimum. And again, that should make sense because if I have a point and to the left the derivative is negative, meaning that we're decreasing to the left, and to the right the derivative is positive, meaning we're increasing, you can see that this is a minimum. This also works if I have endpoints. So let me just put this little note in here. So both of these. So note, if we have a closed endpoint from a closed interval or a half-closed interval, and one side follows the rule. So for instance, if my endpoint is a right endpoint and to the left it's positive, we still get a maximum. So we still get the extrema. And similarly, in this case, if this is a right endpoint, so I'm only coming in from the left, and you see it's negative from the left, this will be a minimum. Okay, let's see two examples. First example is a polynomial defined everywhere. And I want to find all extrema. And the process for this is to generally take the first derivative. So that's going to be 8x cubed minus 24x squared plus 16x. Set the first derivative equal to 0 because I want to find the critical points. I don't need to check to see where this is undefined or the first derivative is undefined because the derivatives of polynomials are defined everywhere. So set equal to 0, 8x cubed minus 24x x squared plus 16x. And I made this example so this works out nicely. I can factor out an 8. I can factor out an x. And then this quadratic factors as, so we have 0 equals 8x, x minus 2, x minus 1, which means we have critical points at x equals 0 from this, or positive 2 from this, and positive 1 from this. I'll keep them in this order. So we found the critical points. And I can actually figure out where they are now by plugging them in. So f of 0, well, that's pretty easy. 2 times 0 to the fourth minus 8 times 0 cubed plus 8 times 0 squared minus 1, so that's going to be negative 1. F of 1 is not too bad, but I'll write it out to show a little bit more work. So 2 times 1 to the fourth minus 8 times 1 cubed plus 8 times 1 squared minus 1. And so this will be 2 minus 8 plus 8 minus 1, so that's going to be 1. And our final critical point, f of 2, and if I put this in, I'm going to end up getting 2 times 2 to the fourth minus 8 times 2 cubed plus 8 times 2 squared minus 1. 2 to the fourth is 16 times 2 is 32. 2 cubed is 8 times 8 is 64. 2 squared is 4 times 8 is 32 minus 1. And this will equal negative 1. Now, I can look at this and get a really good guess that negative 1 being less than 1 means this will be a minimum, this will be a maximum, and this negative 1 again will be another minimum. So that's my thought. Now there's an even better way to check this, and that's with a sign chart. So I'll put this in, I'll put my critical points here, 0, 1, and 2, and I will consider f prime of x, because that's what's going to tell me whether I end up having maximum or minimum. And so if I consider a point to the left of 0, like negative 1, f prime of negative 1 is going to end up being, let me see, now it doesn't matter the exact value of it, it just matters whether it's going to be increasing or decreasing. And when I put this into here, I will end up getting, that's going to be negative 8 minus 24 minus 16. That's going to be a very negative number. I can continue that by, let's say, putting in 1/2, putting in 3/2, and putting in, let's say, 3. Or I can notice, as I cross over the 0, this changes signs, 8x, so this will become positive. As I cross over 1, now this changes signs, so I'll have a positive times a negative times a positive, which is going to be negative again. And as I go over here, this changes signs, so positive times positive times positive is positive. And this will tell me right now that the point 0, negative 1 is a relative minimum because the derivative changes from negative to positive. The point 1, 1 is a relative maximum because the derivative changes from positive to negative, and the point 2, negative 1 is a relative minimum, again, because the derivative changes from negative to positive. Now that's all the first derivative test tells me. However, since I know a little bit more about this, I do realize that this is a quartic function. It's going to be W-shaped. And since I have both of these at the same level, these two will also be absolute minima. Before we go on to the next example, let's take a look at a graph and see if this all jives with what we've talked about. So here's the graph, and clearly you can see it comes down. We get this minima here, this minimum here, and it's the absolute minimum. There's nothing lower than this. There's one other point that's the same level, but they're both going to be absolute minima. Up here at 1, 1, I have a relative maxima. It's only relative because as I go here, it keeps on going up. There is no absolute maximum on this. And then to the right, it goes back down, and I do have a relative and absolute minimum here. All right, last example. find and classify all extrema of g of x equals sine of x on this interval. So let's dive right into this. Same idea. First find the derivative, so I can try to find the critical point. So the derivative of sine is cosine. Cosine x is equal to 0 at pi over 2. And at 3 pi over 2, and it keeps going, but here's the thing. 3 pi over 2 is not actually within my domain, and I'll talk about this when we see the graph, but it's not actually an endpoint. It cannot give me an extreme. So the only critical point is pi over 2, or at x equals pi over 2. When I substitute pi over 2 back into g, I'll get sine of pi over 2, which is 1. I also need to consider the endpoint. And the endpoint I have is 0. And when I put 0 into sine, I get 0. And I can do the same thing with the sine chart to see what's happening. So in here, I have 0, I have pi over 2. If I consider a point here, I'll be a little bit more explicit in this. So let me consider the point pi over 4. That's inside this first interval. I don't care what happens here because it's undefined over here. And I don't need to actually get to this 3 pi over 2. I should probably keep inside here, but I don't need to actually get here because it's not defined here or after. But in this first interval here, I'll consider pi over 4. G prime of pi over 4 is going to be root 2 over 2, which means that g prime is positive on this interval, from 0 to pi over 2. From pi over 2 to 3 pi over 2, let's consider another point. And a nice point in here, I like using as easy of a point as I can. A nice point is pi. And so I'll actually do g prime of pi, which is going to be the cosine of pi. That's negative 1. And again, the only points where g prime hits 0 or might be undefined, well, the only one is pi over 2 on our interval. So it can't change signs anywhere except for here. So it'll be negative throughout the entire interval. And this means that 0, 0 is a relative minimum since g prime is greater than 0 on the right, and pi over 2, 1 is a relative maximum since g prime changes from positive to negative. Now, I know more about this, so the biggest the sign can be is 1. So this is also an absolute maximum. And I also know that if I got to pi, is that the one? No, let's say, I'm approaching 3 pi over 2. Sine of 3 pi over 2 is negative 1. It will drop below this point here, so this will only be a relative minimum. Alright, let's look at the graph. So let me get rid of this and pull up this one. And I do have to talk about why we don't have an absolute minimum here. But first off, we can see we have a relative minimum here. In some interval around this, this is the lowest point. Over here at pi over 2, 1, we do have the absolute and relative maximum. It is the highest point up here, not just in some interval, but everywhere on my curve. But I have no absolute minimum, and the reason is this. This endpoint here is not included. This endpoint here, this not included endpoint, is at 3 pi over 2, negative 1. Which means, as I get closer and closer to this, the curve's going to decrease. And no matter how close I get to negative 1, I can never get to negative 1, it's not included. So let's consider negative 0.9. Well, negative 0.99 is even lower. And negative 0.999 is even lower. And negative 0.9999 is even lower. And for reasons I'm not going to go into right now, negative 0.9 repeating is equal to negative 1. So that doesn't work either. So there's no actual lowest value. So that's why this is only relative. And even though it is bounded, we don't actually get a minimum. This is a greatest lower bound, but not a minimum value. Alright, I hope this helped out. Feel free to comment below if you have any questions.